This video examines the effect of spin upon the shape and surface area of the stationary limit surface of a rotating uncharged black hole. It shows there is a limit to both the flattening or dilation of its shape in the equatorial plane and the increase in surface area it undergoes. Alright, so in previous videos we found the structure of the Kerr black hole to have this form here. And we found that the outer stationary limit is the yellow surface here. The outer stationary limit surface is the yellow one here. The outer event horizon is the red one. The inner event horizon is the green one. The inner stationary limit surface is the blue one. And then we have the ring singularity here of radius A. Coordinate radius A. Now, inside the outer event horizon, we can't observe and determine whether or not this inner structure actually exists. It's just predicted by the mathematics, and we accept that, but we don't have any observational evidence for that. Since we can't see beyond, we can't make observations beyond the outer event horizon. Between the outer event horizon and the outer stationary limit surface is the ergosphere. And we've seen that in previous videos. These are the equations that specify these surfaces, and although they look like an r equals constant, except for the stationary limit surface, these surfaces, as we'll see in this video and the next one, are actually oblate spheroids and not spheres. Okay, now the spin parameter is given by A as J on MC. Now in the literature, what's most commonly quoted is the dimensionless spin parameter, and that's given by A star as JC on GM squared. Now the two are connected by this relation here. A is GM on C squared times A star, and if you were to multiply this object here by GM on C squared, you would see that the gravitational constants cancel. The C up here would cancel, leaving just one down here. This M up here would cancel one of these down here, and then you'd just be left with A as J on MC. So that's how the two are related. Now we can use that relationship to show that the maximum value A star can take is 1, since the outer and inner event horizons are given by this. And so if we substitute A with GM on C squared times A star, we get this expression here. And then what we can see is that in order to keep this real, this value under the square root sign cannot be less than 0. Its minimum value is 0. And so A star can vary between -1 and +1. Anything less than 0, if anything less than 0 here, and we have complex values, and so you have a naked singularity, which according to the Penrose's cosmic censorship hypothesis, that can't happen. So we must keep this real, so square root here, this can come to 0 or greater, that's it. And that means A star then can only be between -1 and +1 because the square of it is positive, and +1 for spin in the positive direction, -1 for spin in the opposite direction. Okay. So that establishes a limit on A star. Alright, so in this video we're going to be concerned with the stationary limit surface out here, and what we're interested in, and the red bit is the outer event horizon, we're interested in the semi-minor axis here, given by this value here, and the semi-major axis, which is given by this value here. So we saw the equation for the stationary limit surface had the cos term in it, and when you put pi on 2 there, 90 degrees here, pi on 2, you end up with this value here. So this semi-major axis is given by this value, and the semi-minor axis is given by this value. This semi-minor axis coincides with the semi-minor axis of the outer event horizon. Okay, so the outer stationary limit surface occurs when this one is GM on C squared plus the square root of this object here. Now, the semi-major axis of the stationary limit surface occurs when theta is pi on 2, as I was just discussing a moment ago. So let's put that in there, pi on 2. Well, cos of pi on 2 is 0, so 0 squared. That term drops out there. We're left with the square root of this, which gives us gm on c squared plus a gm on c squared here. So we get 2 gm on c squared here, the Schwarzschild radius for a non-rotating stationary black hole. Now we see that Rs plus is greater than R plus. Okay, so as we saw in the previous diagram, the semi-major axis is larger than the semi-minor axis. Here we're dealing, of course, with coordinate lengths. Okay, and R plus is, of course, just to remind you, this object here. All right, now the nearest black hole to us at a distance of 1.06 plus minus 0.12 kiloparsecs, according to Cantrell and others, 2010, is named A0620-00. It has a mass of 6.61 plus or minus 0.25 solar masses and a dimensionless spin parameter A star of 0.12 plus or minus 0.19. Just notice the uncertainty is greater than the measurement than the value itself. But anyway, for the sake of argument, we can work with that value. Okay, in 2018, just as a matter of interest, the European Space Agency beamed a signal towards this object in memory of Stephen Hawking and his work on black holes. Now, in the previous video, we found that linear tangential speed of the event horizon to be v is a star c on 2, which is 0.12 times c on 2 is 0.06 c. That's the tangential speed, the linear tangential speed of the rotation. Now, this gave us an angular velocity and number of rotations, while the angular velocity defined t, as we saw in a previous video, as v on r plus, is 927.03 radians a second. And to work out how many rotations, complete rotations per second, we take that divided by 2 pi, gives us 147.54 rotations per second. So this object here, even with a low dimensional spin parameter of 0.12, still is performing 147.5 rotations every second. All right, so let's look at the ratio of the semi-major axis to the semi-minor axis, the different values of spin. Okay, spin 0, no spin at all, so a stationary non-rotating black hole, a Schwarzschild black hole, and the ratio between these two is 1. We just have a sphere. Introduce a small spin, and the ratio now is slightly greater than 1. The semi-major axis starts to be a little bit larger than the semi-minor axis. Let's go up to an extreme case. This is an extreme rotating black hole, the extreme or Kerr black hole. Let's take A asterisk, just for argument's sake, to be 1. Whether or not they actually reach 1 in nature is not clear. But let's just take A star equal to be 1, and the ratio then gives us a value of 2. Now the semi-major axis coordinate maintains a constant value. Along here, remember it was that value we saw of 2 gm on c squared, but it's the semi-minor axis that the r plus coordinate decreases as the spin value increases. Let's look at some examples of this. Let's view this flattening of shape in more detail. So here's our case from the previous page, spin of 0.12. Okay, here's our ratio of the two axes. Now let's introduce the spin to 0.3 and the ratio increases slightly. I've remade this video, you'll notice, because the previous version had 0.33 here, just a typing error, and with this answer, but this answer is for 0.3, and that's what I intended. I'm not sure how the 0.33 occurred there, just a typing error. So I've remade the video as a result. So A star 0.3 gives us this ratio. A star 0.6, this one, increased again. You can see a little bit of flattening beginning to occur. Notice A star 0.9, and we see a bigger ratio again, and the flattening is a little bit more noticeable. And again, as we get to the extremal case, 0.999, it's very close to 2, and you can see a tremendous amount of flattening has occurred. Visually, you can just see there's a fair bit of flattening occurred from about 0.9 onwards. Perhaps it'll be noticeable even from about 0.8 onwards. But anyway, in the very extreme case, at the uppermost limit, whether or not objects actually reach this in nature, we don't know. But A star is 1 and the ratio becomes 2. And you can see a tremendous amount of flattening there. Looks side on, as a spin parameter reaches the maximum value of 1, the ratio of the two axes approaches the value of 2. So A star is 0.6, still quite spherical looking, but even at 0.8 here, you notice there's a bit of flattening going on, and then it won't get any flatter than this. It doesn't reduce down to a pancake or anything like that, but it flattens out quite a bit, but doesn't go entirely flat. So the oblate spheroid shape of the stationary limit surface can only be flattened so far. Now, the poles of the stationary limit surface coincide with those of the outer event horizon below. And so as they decrease, so must the poles of the outer event horizon. And we'll see that in the next video. All right, now an oblate spheroid with z-axis of symmetry of the form we are using here can be described in the parametric form as I've shown in previous videos, satisfying this equation here. Okay, its surface area A is this double integral. Remember, we're in curved space now, so you must consider the metric components in the integral. In flat space, these are just 1. And we'd integrate d phi d theta, but we're in curved space, so we must have the square root here of the area element in curved space, so square root g theta theta g phi phi. And phi we're integrating over 0 to 2 pi, theta over 0 to pi. We have to remember that g theta theta is rho on the surface, on the stationary limit surface, s, it's rho s plus squared is rs plus squared plus a squared cos squared theta. And g phi phi is this object here. Okay, that one there. So the question is now, what happens to the surface area of this oblate spheroid as the spin is increased? We're just going to keep the mass constant. We're just going to look at the same mass black hole, uncharged of course, and we're just going to look at increasing the spin value and just see what effect it has on shape and surface area. Okay, so here spin of 0.12. Here's our surface area here. This is numerical integration device on a software package, so performing a numerical integrate. Numerical integration gives me this value here. 0.3 gives me this one. Again, I had a 3.3 here for some reason, so I've altered that. And this surface area here, increasing spin to 0.6, I get this one. Okay, notice the surface area has increased a little bit. A star 0.9. Now in the previous video I had where the 4 is, I had a 3. So again, a typing error. So second reason to remake this video. So A is 4 point that, not 3, 4 point that. Notice how it's increased a little bit. And then for the extreme case, 0.999 gives me this area here. And for the very extreme case, for the absolute upper limit, A star is 1, we get this here. So there's a little bit of an increase in surface area for the same mass. So as the spin increases to its maximum value 1, the surface area of the stationary limit increases by a small amount to some maximum value for any given black hole mass. All right, for our example, the percent increase in surface area is about 4.37%. Now, as a semi-minor axis of the stationary limit surface decreases, so too does that of the outer event horizon, because if the semi-minor axis for the stationary limit surface is decreasing in the z-axis direction, then the outer event horizon must be compressed as well. And that increases the ellipticity of the outer event horizon. We expect that, and we'll see that in the next video. Now, that suggests that the surface area of the outer event horizon similarly increases as its spin increases. Now, I need to explain that here. This statement here, this dot point, is true because if the mass of the black hole itself is increasing, because when you think about what causes the surface area of a black hole to increase is the mass. It's related to its mass. And what causes the spin to increase is matter and energy falling onto the black hole and increasing its angular momentum, such as when you have an accretion disk around the black hole and matter and energy are crossing the event horizon, then you're increasing the mass of the black hole. So this statement here, and I didn't explain that fully in the last video either, but this statement here is on the understanding that matter and energy are crossing the event horizon, and that is what is increasing the spin. Black holes don't suddenly increase their spin because they feel like it or because it's a good idea or what have you. There's some mechanism by which that happens. And what happens is matter and energy flowing across the event horizon imparts angular momentum, more angular momentum to the black hole and increases its spin. So this statement is to be understood. Surface area increases because matter and energy are crossing the event horizon, imparting angular momentum to the black hole itself, and so increasing its mass. And we'll see that in the next video. Now, the entropy of a black hole is proportional to its surface area, according to entropy is AC cubed on 4g h bar. And Stephen Hawking's area theorem says that the area of the event horizon cannot decrease in transformations. In any sort of interaction, it can't decrease. So recently, evidence has been found to support this theorem. And the evidence came from the gravitational waves given off by two merging black holes, from which it was possible to compare the surface areas before and after the merger. So the two objects that merged, the surface areas and masses were known beforehand, and then it was possible for these researchers after the merger to calculate the new surface area of the new object that was formed. They have confirmed, as in their own words, we have confirmed that the GW150914 data agree with Hawking's area theorem with high probability greater than 95% or 2 sigma, EC and others, 2021. All right, so surface area does increase, it does not decrease. The microquasar GRS 1915 plus 105 contains a 12.4 solar mass black hole with dimensionless spin parameter A star is 0.98 plus or minus 0.01. That's Reed and others, 2014. If you look up that paper, you can see the result there. That's an extremal case here, 0.98. This gives it a linear tangential speed of 0.49 c, and how that was calculated is shown in the previous video. Now, for the black hole GRS 1915 plus 105, we have an angular velocity and number of rotations per second of, while the angular velocity defined in t is v on r plus, is 6,707.48 radians per second. Quite a lot. And to see how many complete rotations that is, divide by 2 pi, and you get 1,067.53 rotations per second, which I just think is a phenomenal number. Something with 12.4 times the mass of our sun compacted into a small space but rotating it over 1,000 times per second is just phenomenal. It's really just amazes me every time I look at this number. All right, so here's our model of the stationary limit surface of GRS 1915 plus 105, and here's the flattening that occurs. So looking from above, off-centered from above, and looking side on, you can see quite a bit of flattening. Now, the supermassive black hole at the heart of the quasar Q2237 plus 305 is a mass of 1 billion solar masses and a dimensionless spin parameter A star of 0.74, according to Reynolds and others, 2021. Looking from above, you can see it's quite spherical. A little bit of flattening has occurred, but not too much. And side on, you can it still looks quite spherical, although a bit off spherical. But you can see there's a little bit of flattening there, but not as much as the one above, GRS 1915 plus 105. Wow, difference. It's really up in that top range of spin values that the flattening really occurs. All right, Cygnus X1 has a mass of 21.2 solar masses and a dimensionless spin parameter of greater than 0.9985. That's Miller and Jones and others, 2021, if you look up that paper. And you can see the flattening is noticeable. The stationary limit surface here is just phenomenal amount of flattening here, because that's a really extreme case. And you contrast that with Sagittarius A star, the black hole at the center of our own galaxy, the supermassive black hole at the center of our own galaxy. It has a mass of 4.2 million solar masses, 4.2 million times the mass of our sun, and a dimensionless spin parameter A star of 0.44, a bit more pedestrian. And it's quite spherical looking. It's hard to notice any real difference, really quite spherical looking. Okay, that would be that. Job done.